sample hypothesis testing. So I want to have a brief review about what we talked during the last lecture. So when we talk about hypothesis testing, we always put that in the framework of a null hypothesis and alternative hypothesis. This is a little bit counterintuitive because the null hypothesis is what you start from, and also it's a distribution that you work out your p-values, etc. However, the null hypothesis is really what you were hoping to reject. And your research hypothesis or your research belief is really more likely to be framed in the alternative hypothesis. And so understand this distinction between null hypothesis and alternative hypothesis. And then we introduce the 4 possible scenarios from hypothesis testing. The 4 possible scenarios comes from that 2x2 table where what is it true, whether it's null or the alternative hypothesis, and then what is your decision. So those 4 scenarios has 2 possible errors. The first error is type 1 error, which means that if the null hypothesis is true, however, you reject, your decision is to reject the null hypothesis. So in that case, you are making a type 1 error. And we also talk about type 2 error, which means that if the null hypothesis is incorrect, if truth is the alternative hypothesis, however, you fail to reject the null hypothesis, and in that case, you are making an error again, which is called the type 2 error. And from the type 2 error, we get the idea of a power. A power is 1 minus the type 2 error rate. So the power refers to the probability that when the alternative hypothesis is correct, the probability that you reject the null hypothesis. Essentially that this is the one quantity that when you design your study, you would like to maximize your power. Essentially, if the data comes from the alternative, you would like to maximize the probability that from your data to reject the null hypothesis. So after we talk about those concepts, the one detailed test that we introduced specifically last time is one sample t-test. So what is one sample t-test used for? It is used for when you are performing hypothesis testing on the population mean, and you do not know the population standard deviation, or you do not know the population variance. In that case, you obtain a sample and you estimate a sample mean. And based on the sample mean, you establish a one sample t-test. And you refer to the one sample t-table. You will refer to the t-table to get the p-value. And you make your decision from there. So that is called one sample t-test. And in that process, we also introduced the concept of p-value. What is a p-value? A p-value is really a probability. And it also, remember, it is a probability that always estimated under the null hypothesis. So what is this probability? It is a probability of observing the observed statistic or even more extreme under the null distribution. So that is p-value. So after we talk about p-value, we basically said that there are 2 equivalent ways to perform hypothesis testing. The first one is to, based on the alpha level, you select a rejection region. And then if your observed statistic falls in the rejection region, you reject the null hypothesis. If it doesn't fall into the rejection region, you fail to reject. And the second equivalent way is from your observed statistic, you estimate a p-value that corresponding to that statistic. And then you compare the p-value with alpha that you prior specified. And then if the p-value is larger than alpha, you fail to reject. And then if the p-value is less than alpha, you reject the null hypothesis. So this essentially is what we introduced last time. By the end of this lecture, what we are going to talk about is two population hypothesis testing. So for this lecture, we are going to talk about also on population mean. So the difference between this one and the previous lecture is previously we are talking about one population mean. So comparing a population mean to a specified value, specific value. For example, comparing the birth weight of a low social income area of baby birth weight to 120 to a specific value. So for the context of today's lecture, we are going to talk about you have two populations. For example, you have the population that the baby birth weight coming from the low social income area. And then you have another population which is the baby birth weight coming from a different area, let's say high social income or just general. That doesn't characterize by the previous character. So if you have one sample, if you have a random sample from each of the population, let's say your sample size is 100. So essentially you are comparing 100 baby birth weight compared to another 100 baby birth weight. So in this case, you are talking about whether the population mean are the same or not the same between the two populations. So that is the hypothesis testing lecture 2 that we want to discuss today, which is performing hypothesis testing on population means from two populations. Any questions before I move on? Yes. Okay. So when we talk about comparing the means between the two populations, there are one fundamental distinction between the two scenarios. The first one is if the two populations are completely independent, which means they are independent of each other. And the other type of scenario is the two populations are kind of related. So depending on which scenario it is, actually we need to use different hypothesis technology for to handle the two different questions. So the two sample inference, which refers to the two population inference, there are these two possible scenarios. In statistics, sometimes we call the independent samples, we call two independent populations. For related samples, we call paired samples. So I gave you a little bit example here is what we mean by paired samples or what do we mean by related populations. So for example, if you have a single population and then you take some treatment on this population or you observe something that happens in this population. So for that case, you would like to see what is the impact of this event or what is the impact of this treatment on this population mean. So essentially, if you put that in a time scale, that is before and after measurements. So you're comparing the population mean before and after an event. So this is what we call a typical scenario of related population. Because for each sample in this population, you have a before estimate and then you have an after estimate. Remember, these two estimates or these two random numbers are not independent. And the second possible example is, what if you have two related populations? So in this one, from epidemiology study, quite often people carry out matched pairs. Essentially, if you want to compare the difference between two populations, and you want these two populations to be as similar as possible by control or by design. And you want that the only biggest difference, the only difference is what you are is a factor that you are interested. For example, you want to compare between, you want to compare, like, see, people who take the drug, their blood pressure compared to people who do not take the drug. However, you know that blood pressure is influenced by age and BMI. So in that case, when you design the study, you really design that, you design by pairs. Essentially, if you have in your sample, in your first sample, which is a 35 years old male with a BMI 30, and in your second sample, who is taking the treatment, and then in your second sample, you would like to have also a 30-year-old male with the same BMI but not taking the treatment. So essentially, you have some intervention in terms of when you're sampling. You really have a matched sample. So in that case, it's also related population. A third example, which is not listed here, is you quite often encounter when you do genetics or some genomics experiment. For example, you would like to see that whether a certain environmental factor have an impact on the population mean. And what you do is sometimes you take paired study from the siblings. So you take one sibling that have the exposure of the environment, and then you take the other sibling that doesn't have the exposure of the environment, and then you compare their difference. The fundamental rationale behind the sampling technique is that you would like them to share as much as their genetic background. So in that way, each sample comes in the unit of a pair of siblings, and those pair of siblings, of course, they are not independent. And a lot of times you can also see in clinical trials that they put treatment on one eye, randomly select on one eye, and then the other eye for the same individual doesn't have the treatment. So that is also called a paired design or paired randomized design. So in that case, remember, for paired design, the key is your sampling unit is always in pair, and the two individuals or the two samples within a pair, they have some correlation.
I don't know if you mentioned, but let's say two identical twins definitely independent, but what about fraternal twins? Are they not independent?
They're not independent, they're dependent, because although they have some genetic difference if they're not identical twins, but they share some of the household impact, and they share some genetic information. So essentially, as long as they have some correlation, it's called dependence. It doesn't have to be exactly the same genetic background. So here there is an example that, so for this one, it's really to help you to think about, for the same question, for the same scientific question, you can actually design different study to answer the same question. And each design has pros and cons. However, each design requires different statistical technique to analyze the data. So for example, if you're interested in the relationship between the use of oral contraceptive and the level of blood pressure in women, you could have all different designs. So the first design, which is probably the most straightforward design, is to see, suppose you just random sample blood pressure from a woman that taken this OC, and then you do the same thing for another random sample for the woman that do not take the OC. So for this one, because you random sample the first sample and the second sample independently, So they really coming from two independent samples. And also, those are really representing the two independent populations. The population that use the OC and the population that does not use the OC. So in that way, in epidemiology terminology, we call this is called cross-sectional study. Each patient or each sample come at one visit to measure their blood pressure. So the advantage of this design is it's very simple to carry out. It's very easy. The disadvantage is if you observe the difference in terms of the blood pressure between these two populations, there are a lot of confounding factors. For example, it might be that your first OC user sample have a higher age compared to the second sample. Or it might be that they are on average more obese than the second sample. So essentially, this type of design is very prone to confounding factors. The second design that you can also think about to answer the same question is, suppose you have consent form to a group of non-OC users, and you ask them to participate in this study, and you ask them that this study, they will take their blood pressure when they come into the first visit, at the condition that currently they are not taking any OC. And then you give them OC, and they take OC. After they take OC for a while, they come back to give you a visit, and then during that visit, you measure their blood pressure. So the advantage of this study is the data is cleaner, because if you think about it, in this time, your data is really coming in pairs. For each individual or for each woman in your study, you have a before OC blood pressure and you have an after OC blood pressure. So the difference is relatively more cleaner that attribute to OC usage, because they are the same woman and they basically have the same age, same BMI, same lifestyle. So if you observe some difference in terms of their blood pressure, you have more confidence that it's less biased or it's less possible to be biased by confounders. The disadvantage of this design is you might lose the follow-up from some patients. So suppose they do not come back in the second visit. In that way, your first measurement of that woman on blood pressure becomes useless to you. So for this one, you will have the risk your sampling is essentially harder. Okay, so for the third design, or for the third idea of design, is you can see that because I know that blood pressure really depends on not only the OC usage, but also on the other factors. So I do a match design that I match my samples as much as possible, except that one sample uses AC and the other sample do not use AC. So I match them on age and weight. So in that way, whenever you have a 30-year-old woman with a weight 120 pounds that uses AC, you try your best to recruit another 30-year-age woman that with the same weight but doesn't use OC. And then you can see that your sample also comes in pairs. And then this represents the paired samples from two related populations as well. So we talk about those three designs, and you can think about it that the first design is talking about the population mean of two independent populations. And the second and the third one really talking about the population mean of related population. Okay, so we first wanted to introduce the paired t-test. So paired t-test is really used to answer the questions of the first scenario, which is estimate or hypothesis testing the difference in population means from the two related population. And so the essential idea of paired t-test, or this hypothesis testing technique for paired population, essential idea is instead of comparing the two populations directly, you estimate the difference on each individual level or each pair level, and then you test the difference. You compare the sample of difference, you compare that the population of this difference, whether the population mean of the difference is equal to 0 or not. So this goes back to a one sample t-test, or to a one sample hypothesis testing. So this is the essential idea. We will give you more details later on. But before that, we want to talk about what is the assumption. So remember here, we're using a t-test. So t-test is assuming normal distribution without known population standard deviation. So in that case, you know that there is assumption that either the population, underlying population, is normal distributed, or if you are not comfortable to assume the normal distribution, you have to have a large enough sample size in order to use central limit theorem. Right? So this assumption, I hope it's becoming more and more clear to you when we get along with this lecture. Okay, let's go back to the same example, that to study the effect of OC on blood pressure. Suppose we have, in our sample, we have 10 women, and they're not currently using OC. We measure their baseline blood pressure when they're not using OC, so which is this column right here. And then we give them a constant form, and each of them is using the OC in the next year. And after a year, we ask them to come back, and they take the blood pressure again at the second year visit, which is this blue column. So suppose in the ideal situation, we don't have any missing data. We have every woman come back for the same study. So we have exactly 10 multiplied by 2, 20 data points, and that is taken from 10 individuals. So in that way, your data essentially comes with those two columns. Remember, a very convenient way to assess mathematically whether this is a paired design or not paired design is whether or not you can put the data in symmetric columns. So let's say before and after. Let's see, matched sample 1 and matched sample 2. You can always put that in matched columns. If you can do that, most likely it confirms that this is a paired design. If you cannot do that, most likely this is not from a paired design. So suppose we have this blue column and have this green column representing this blood pressure when they're using and not using OC. So how do we perform the hypothesis testing on whether the mean of this population is the same with the mean of this population? We can, of course, do that, just comparing, just ignore this parent relationship, just comparing this versus this. However, this is not as efficient as the paired design, which is basically mean that instead of comparing column versus column, what you do is you look at each woman and you get the difference of their blood pressure change before and after. So 128 is after they take OC, and you subtract 115 is the blood pressure that of the same woman that they do not take the OC, and you get a difference of 13. Why do we do that? The rationale, like what I said, is really that we assume the difference between 115 and 128 is really more likely to caused by the OC usage, because for the same woman, she doesn't change that much in terms of her lifestyle, her weight, and her age, and her genetic background. So every possible confounding factors is more likely to be controlled if you take the difference. So you take the difference, and then you got a difference estimate. And you do the same thing for the other non-women. So essentially, you got from this 2 column, you reduce the data into 1 column. And this 1 column now is not the blood pressure before or after. It's really the blood pressure that the difference in the blood pressure by taking the UC in that 1 year. So essentially, you got this 1 column. And if you think about it, now the question is whether the blood pressure for the OC user is the same with the blood pressure for a non-OC user. So if you translate into that hypothesis testing into this column, that is equivalent to whether this difference is equal to 0 or not. So essentially, the paired t-test is you take the difference within each pair, and then you perform a 1 sample t-test on the difference. And then the null hypothesis for this test is 0, because if the difference has a mean 0, that means before and after they have the same mean. So this is a trick. Essentially, you're taking the difference within each pair, and then you test the mean of this difference, whether it's equal to 0 or not. And then, similarly to before, we do not know the standard error or the variance of the difference. So sigma d is unknown. So we can estimate that. How do we estimate that? We estimate by sample standard deviation. So sample standard deviation is really if you take the mean of the difference, and then you take the summation of the squared distance from each observation to the mean, and then you divide it by n minus 1. Remember, here is n minus 1. And this is quite a point that a lot of people make a mistake. What is this n here? This n is the number of your pairs. Remember, in the 2-sample paired t-test, the sample is organized by pairs, and your degrees freedom is n minus 1. And n is not the total sample size, because the total sample size should be the total pair size multiplied by 2. However, what is really the degrees freedom for a 2-sample paired t-test is the number of pairs. And if you think about it, what we talked about before, it actually makes sense because you reduce the data from 2 columns to 1 column. And essentially, you're just testing this 1 column. So this 1 column, you have only n equals to 10 instead of the original sample size that you have 20. And then after you have this S estimate, you can derive a T statistic, which is D bar, that is the mean of the difference, subtract the null hypothesis value, and over the standard error, which is what you estimate here, over square root of n. Most likely, or most of the time, this null hypothesis value is 0. Okay, and after we know that, the rest of the stuff is really review. So hypothesis testing for mean difference, when sigma d is unknown, there are 3 scenarios. One is a two-tail test. Essentially, the null hypothesis is whether the null hypothesis is mu d equals to 0, and the alternative is mu d does not equal to 0. So in that case, your rejection region is distributed in both sides of the x-axis, and you got alpha over 2 from each side. And then you also have an upper tail. In that case, your alternative hypothesis is mu d is bigger than 0. So if you taken the mean by after subtract before, that essentially means that you think this OC treatment actually make people improve or increase the blood pressure. So that is the scientific translation. And for this one, your alternative is mu d less than 0. So essentially it means that this OC usage decreases the blood pressure. And for each of the tests, you have the rejection region right here. So suppose we put some numbers in our example. We have 10 pairs. We have 10 women, and sample size equals to 10, and each one gave you a before and after. And we take the difference. So this is our data. So in that case, we estimate d bar, which is the mean difference, is the average of the D column. The average of this column, which is 4.8. And then we estimate the standard deviation of the difference is by this formula, which is 4.56. Okay? And suppose we have a two-sided hypothesis testing scenario, which means the alternative hypothesis is whether there's any difference in blood pressure caused by the use of OC. And suppose the alpha equals 0.01. So in that case, what is the critical value? The critical value should be a t distribution with 9 degrees freedom, and then each side should be alpha over 2, which is 0.005. So if you go to a t table, if you go to an R function, it tells you that critical value is 3.256. So what does that mean? That means that if the observed t is bigger than 3.256 or less than negative 3.250, you reject the hypothesis, the null hypothesis. If the t is within those two critical regions, those two critical values, you fail to reject. So what do we have here? The t statistic, if we plug in that formula, we got mean, which is 4.8, subtract 0 over 4.5 over square root of 10. So in that case, we got 3.32. So if you map the 3.32 in this graph, you got 3.32 is right here. So what does that mean? That means the t is in the rejection region. So your conclusion is we reject the null hypothesis. And the scientific conclusion is there is a significant change in blood pressure that's caused by OC usage. The next thing that we want to talk a little bit about this is from hypothesis testing, you can also estimate a confidence interval. And the concept of confidence interval, we talked the other day when we have the lecture on estimation. So confidence interval is really, if you believe central limit theorem, this t, it follows a t distribution with 9 degrees freedom. So if that is the case, you can derive the confidence interval for d bar under that assumption. So exactly how do we do this? So remember, t equals D subtract mu over S over square root of N, and this follows a T distribution with n minus 1 degrees freedom. So that means probability that this T less than is bounded by these two critical value is 1 minus alpha. Is that correct? Essentially, this is a distribution of Tn minus 1, and then this part is alpha over 2, and this part is alpha over 2. So the area that bounded within these two critical value is 1 minus alpha. So essentially, the probability of this number that bounded within this two value within this two critical value is 1 subtract alpha, right? So if you place this in terms of this T, what you get? So you put this term right here, and this is what you get, right? Replace this term by this whole term right here. Remember, this mu is not your hypothesized value. This is really a review. When we talk about this is when you talk about estimation of the mean of that difference. So essentially, what you want to get is what you want to get is the probability of this actual mean is bounded within this two boundary have probability of 1 minus alpha, right? So that tells you that the confidence interval of mu is from here to here. So this is the confidence interval right here by this formula. So if we plug in those numbers, what we get is this mu is 1.5 and 8.0. See? So this is the confidence interval for mu from the sample. And so we talked about two different ways to perform hypothesis testing from last time lecture. One is by the rejection region, and the other one is by p-value. So here, actually, we give you a third approach to perform hypothesis testing. So what you can do is you can do a confidence interval estimate based on your estimate. So in that way, you can see that the way that you construct your confidence interval really doesn't matter with your hypothesis testing, because here the mu is a true population mean. It doesn't matter whether This is your null hypothesis or your alternative hypothesis. So here, it's really about estimation. So what essentially tells you that from the sample of 10 women before and after, you can estimate that the difference of blood pressure lies within those two numbers with a probability of 1 minus alpha. And this one is actually alpha equals to 0.1, so this is 99% of confidence interval. Okay, so why do I say that you can use this to perform hypothesis testing? That is because in our hypothesis testing, we're testing that whether mu equals to 0 or not, right? So if that's the case, if you estimate the confidence interval and then you can compare to your null hypothesis and you find that, well, 0 is not in this confidence interval because my confidence interval is from 1.5 to 8.0. However, mu0, which is 0, is outside of this confidence interval. So if that is the case, you can reject the null hypothesis at this alpha level. So this is a summary of what are the 3 ways to perform hypothesis testing. The first way, essentially to test H null mu equals to mu0. The first way at alpha level is to construct a rejection region from alpha. Remember, the rejection region depends on alpha because, remember, this critical value is specified by alpha, right? So construct a rejection region from alpha, and then you compare your test statistic. If it's within the rejection region, that is equivalent to reject H null. Okay, so to be more specific, to construct the rejection region from alpha, it's really under H null. Okay, so this is the first way. Under the H null, the mu0, you construct a rejection region C alpha, and then if your observed statistic is within here in the rejection region, you reject. So this is what we have taught. And the second way is you construct a p-value from under H null based on or from your test statistic. So what does that mean? It means similar sim. With the same mu0, which is your null hypothesis distribution, if this is what you observe, your t, you estimate what is the distribution here. So this distribution gives you the p-value, right? And then how do you make your decision? If p-value is less than alpha, that is equivalent to you reject H null. So this is the second way. The third way, which we talked about today, is you construct a confidence interval of alpha level of 1 minus mu. So for this one, remember, you construct a 1 minus alpha, which is consistent with this alpha. So it still depends on alpha. But for this method, it doesn't depend on your null hypothesized value. Right? You really just, based on what you observed, based on this t, you're really just trying to construct what is the true mean, what is this true mean estimation, and what is this true boundary, the CI low and the CI higher upper boundary that contain this true mean at this 1 alpha level. Okay, so this one, the third method, it doesn't really relate to the null value. So previously, you always construct under the null value. For this one, no, it doesn't have to be. It's just based on your t, you can estimate this distribution, and then you can construct the confidence interval. And then, essentially, you're comparing your mu0 with the confidence interval that you just estimated. If mu0 is outside of your confidence interval, that means based on what you observe from this test statistic, it's unlikely that it's coming from this mu0, so you reject the null hypothesis. And if mu0 is within this confidence interval, you fail to reject. So how do you make a decision? If mu0 is within the confidence interval of 1 minus alpha, it's not within this. You reject the null hypothesis. So those are the 3 ways to perform a hypothesis testing of the same hypothesis at mu0 and at alpha. So essentially, all those are based on the same test statistic. For example, p statistic. Because all those are based on the same, you need to base on the distribution. The first 2, the distribution is centered around your null hypothesized value. And this last one, it's just centered around the true value. Okay? So, those 3 decision criteria, you don't have to worry about any inconsistency between those 3 because mathematically they are all equivalent. If you reject the null hypothesis from the approach 1, you should expect that you will reject the hypothesis, the null hypothesis, from the other 2 approaches. But those are essentially the 3 approaches that you can perform hypothesis testing. And the last one, which is practically most people use if you use a statistical software. For example, you use R. I'm not sure about Python. Do you have a function? But in R, you call t-test, t.test. And then you put in your sample 1, and you put your sample 2 right here. And then it gives you, first of all, it gives you what is the p-value. It also gives you a confidence interval. It also gives you the null hypothesis, and it also gives you a decision. So this is essentially, like in practice, how do you do that? But understand the 3 rules would really help you in order to read the output from any statistical software. Okay?
Number 3, sort of like, what's the probability of getting the null hypothesis given your population?
Kind of. I mean, number 3 is really like, it's about estimation. It's like from my sample, like if I repeat my sample, what this mean would look like if I repeat 99 times or 100. If I repeat 100 times, 99 times the mean will be, the population mean will be within this region. And then you see that because this null hypothesis value is within this region, so I fail to reject. And then if the null hypothesized value is outside this region, so I conclude that it's unlikely that the sample is from this hypothesized value. Yeah. So this part we didn't talk about last lecture because this is really review. This is review of what you learned in the estimation lecture. Okay? Okay, so after we talk about the two dependent samples or two dependent population, essentially what we have introduced today is really when do you use a paired t-test. And remember, paired t-test, although this is a new technique, it's essentially the same with one sample t-test because it's paired t-test, essentially it is a one sample t-test on the difference. So the next thing which is the main topic today is what if the two populations are completely unrelated and they are independent. So sample selected from one population has absolutely no effect on the samples that selected from the other population. And the goal is I want to see whether the I want to perform a hypothesis testing that whether there's any difference between the two population means. So here, if we see we want to estimate the difference between the two population means, a very intuitive point estimate for that population parameter is actually the difference in terms of their sample means. This is fairly easy to understand because the point estimate for each population mean is sample mean, is a corresponding sample mean. So the difference between the two population means would be the difference on the sample means. And for this one, for the difference between the two population means, and suppose they're coming from two independent populations, there are actually three scenarios that if you think more carefully. The first scenario, and all those three scenarios are in terms of the sigma or the standard deviation of each population. So the first scenario, which is the simplest one, what if someone gave you a variance estimate of the variance of each population? This is rarely happen. I mean, most of the time you're trying to estimate. So the first scenario is really the impractical scenario. And if that is the case, you can use a z-test statistic. We can come back to that later, but for this lecture, we are going to talk about we're going to more focus on what if your sigma 1 and sigma 2 are both unknown. So you don't know the variance of each population. So in that case, you have two choices. One is you are willing to make additional assumption that although I do not know the population variance, I assume they are equal. So this is one scenario. The other scenario is, well, I do not know the variation of each population, and I'm not comfortable to make that assumption that they are equal. So essentially, I need to estimate both of those separately, and I do not want to assume that they are equal. And based on these two different scenarios, actually there are a slight difference in terms of how do you perform hypothesis testing. So the first one, what we see is it's a t-test with a pooled standard deviation estimate. And the second one, it's also a t-test, but it's a separate variance estimate. So you can see that when the sigma is unknown, the underlying test statistic is always t-test. So it's always two sample t-test. However, there's slight difference in terms of whether or not you want to make that equal variance assumption. If you want to make that equal variance assumption, it's a two-sample t-test with pooled standard deviation estimate. If you're not want to make that assumption, it's a two-sample t-test with separate variance estimate. So the underlying, the whole framework is the same. It's t-statistic. But how do you exactly estimate the t-statistic is slightly different. So we talk about this first.
I have a question back to this. So say you're designing an experiment and you have your two treatments. And if you're able, let's say by some miracle you're able to understand the variance by taking 30 samples of your non-treated, 30 samples of your treated, and then use that data to then construct like so that you know sigma 1 and sigma 2. Then you could, if you redo the experiment with your treatments, let's say somebody else does it at a different time, they could then use those parameters that were the...
No. Here it's not about you get whether or not you have an idea of the variance. It's really about you're testing the difference in terms of the mean from the two population. And then you need to know the exact standard deviation of that specific two population. So, whether or not you can borrow from prior knowledge or prior experiment doesn't really help you. You're really just comparing your sample as is.
So what is an example of when you would ever know the sample size?
Good question. That is why we very, very rarely introduce this. I mean, in practice, I have never seen any situations that you have a known population variance. I mean, the only thing that we want to introduce here is, suppose you have a large enough sample size. Suppose your sample size is like 100 or 1,000. In that terms, I mean, even if you use a sample estimate of your standard deviation, in practice, it is the same with you use a z-test. Because in that case, you just have so large sample size. So, I mean, your sample estimate of the standard deviation is very close to the true standard deviation. I mean, even in that case, even if you use a t statistic, it's probably in practice, it's the same with a z statistic, right? Yeah.
So when I make heat maps, for example, of large scale changes in genes, is a z-score to normalize all my samples across the genes.
Yeah.
So I have thousands and thousands of genes and many samples. So in that case, we use the z.
I think you are confusing about the concept of standardization and using normalizing. I mean, using statistical tests, because whenever you use a heat map, you said you want to normalize. Essentially, you just wanted to standardize, right, to get a z-score. Here we are talking about comparison or hypothesis testing is specific. So we're not talking about standardization of those kind of things. But you're right that most of the time in that situation, it assumes that the sample is large enough that after you do the standardization, it follows a z distribution, which is essentially assuming that the sample size is very large enough. Yeah. Okay. So here, suppose we have two independent samples from two independent populations, and we want to compare their mean, whether there's any difference in terms of their mean. So the setup is all the same, that you have 3 scenarios. The null hypothesis is their mean, the 2 population mean are the same. And the alternative, depending on what is your question, you could have a 2-sided hypothesis testing, which is mu1 doesn't equals to mu2, or you can have a 1-sided hypothesis testing, whether it's on the left side or on the right side. Okay? So here I gave you the rejection region for each of the scenario. Remember, for 2-sided test, the rejection region is distributed across the x-axis, the positive and negative side, and you have a alpha over 2 on each side. Okay, so we're in this scenario that we do not know sigma 1 and sigma 2, and we need to estimate that. And suppose we want to assume, we are willing to make the assumption that although sigma 1 and sigma 2 is unknown, but we are willing to make the assumption that the 2 population only differs in mean, doesn't differ in the variance. So samples are randomly independently drawn from each distribution, and distribution are normally distributed, or both of the sample size is at least 30, which means you need to use central limit theorem. And population variance are unknown but assumed to be equal. So if you assume to be equal, what is the population variance? What is the estimate of that? So basically, the rationale underlying this estimate is fairly simple, which means that if you assume it is equal from each population, we use a pooled variance to represent the common variance of each population. So we call that SP squared. So SP squared, how do you estimate that? That is n minus 1, that is a weighted average of S1 squared and S2 squared. And S1 and S2 are the standard deviation estimate from each sample. So if you look at this one, this is fairly easy to understand, because if you're willing to assume that the 2 populations have the same variance, then most efficiently, you would want to pool all the samples to give you a common estimate of the standard deviation. So essentially, if you have S1 squared estimate from your first population, you multiply by n minus 1, and so that term is a summation of the mean squared distance from the first sample. And then you take the summation of the mean squared distance from the second sample, and you pull them together, and your total degrees freedom is n1 minus 1 plus n2 minus 1. So here, remember, although we are assuming that the sample, the population variance are different, are the same from the 2 populations, it doesn't have to be that the sample size are the same. You could have different sample size, N1 and N2. It's just that you can pull them together. You can pull all the samples together to give you a SP estimate.
So I actually have a question on this, and maybe we'll get into it. So if you do your experiment and then you have multiple values, you have your variance for your treatment, you have variance for your control. Do you then sort of test to see if the variances are equal for both of them, and therefore you can, pool them? How does that work?
That's a good question. I mean, there's a test to do that purpose. It's called F-test. So F-test is really testing the equality of the variance from the 2 populations. So it's symmetric. So it's very similar to your testing for equality of the mean, you use t-test. And then if you're testing quality of the variance from the 2 populations, you use F-test. So you could do that. I mean, you could have S squared 1, S squared 2, and then based on those 2, you perform an F-test to test whether sigma squared 1 equals to sigma squared 2. In practice, people seldom do that because F-test is known to have very, very little power. the power is very limited. So unless you see a dramatic difference between S squared 1 and S squared 2, most likely you'll fail to reject the null hypothesis that sigma 1 squared equals to sigma 2 squared from an F test. So, I mean, you could do that, but still people just think like the power is so limited. And in this case, I mean, we're not going to go that depth. So we're just talking about whether or not conceptually you would like to make that assumption or not. Yeah, yeah. And also when you see your data and you see that for some reason the S squared 1 is very, very different from S squared 2, in that case, you want to be a little bit cautious to make this assumption. So after you have that SP estimate, which is a pooled variance estimate, what is the test statistic for mu1 minus mu2? So this is a T statistic again, and the numerator is really X bar 1 minus X bar 2, which is a sample estimate, the difference of the sample mean estimate, subtract your hypothesized value over this standard error estimate. And this standard error estimate is SP squared multiplied by 1 over N1 plus 1 over N2. So there's quite a bit of symmetry between the 2-sample t-test and the 1-sample t-test. If you think about it, everything is actually fairly symmetric because previously, and this will help you to memorize those formulas as well. Previously, from one sample, remember our T equals X bar minus mu over S over square root, like this, right? So essentially it is X bar minus mu S over square root of n, right? So in 2-sample, same variance, it's actually fairly symmetric because now the only difference is instead of 1 sample where you just have 1 X bar, you have X bar 1 minus X bar 2, and this is what you want to test, right? And then instead of this 1 mu, you now have mu1 equals mu2, which is your hypothesized value under the null, right? And then previously, you have S squared here, which is coming from this 1 sample, and now you just have a SP here. So that is the pooled estimate. And previously, you have a 1 over n here, and now you just have, actually you just have 2 components of this statistic because you have got 1 component of x1 and x2 bar. So this is the variance, or this is the standard error of this term, and this is the standard error of this term. And then because it's a variance, so it's always on the plus scale. So it's very symmetric to what we had before, and that will help you to memorize. And then if you further simplify this a little bit, you can get that right. So you just pull this out, and you got 1 over N1 plus 1 over N2. So this is the T statistic that to test a 2-sample t-test under the same variance assumption. Okay, so this is the confidence. The next slide gives you the confidence interval, which is also quite symmetric to what we talked before. So let's put that into an example. Suppose you got the same example, but suppose now you take the first experimental design or take the first study design method that you don't really care about the blood pressure changed by the other factors, you first get a sample size of 8 women that takes OC, and then you perform a second sample, the second sampling, and you obtain 21 women that doesn't take OC. And you measure their blood pressure, and you get a sample mean, which is the mean blood pressure of the first group and the mean blood pressure of the second group. And you get a sample standard deviation of the first group and the second group. So this is answer the same question, however, use the first study design. And assume both population approximately normal with equal variance. Is there a difference in terms of the average SBP? So, like we said, we have a formula or we have a recipe to perform this statistical test. It starts with frame your null hypothesis. So your null hypothesis is mu1 minus mu2 equals to 0, and your alternative, you just care about the difference. So it's a two-sided alternative. Mu1 minus mu2 doesn't equal to 0, and alpha equals 0.05. So remember, in this time, for two sample t-tests, the degrees freedom, when you are willing to assume equal variance, degrees freedom is n1 minus 1 plus n2 minus 1. So it's 27. And then if you go to a t distribution with 27 degrees freedom, you got this critical region, which is negative 2.0 and positive 2.0. Okay, so what is your test statistic? Your test statistic, based on that formula right there, is the difference of x bar 1 and x bar 2, subtract this 0 value, and over this pooled standard error estimate, which is right here, and SP is estimated by the previous formula right here. So you got this whole value, this whole t value equals 0.74. Okay, so if you think about 0.74 in this distribution, it's right here in this region. So it's really a non-rejection region. So in that case, your decision is you do not reject at alpha equals 0.05, and you conclude that the mean blood pressure of the OC user and non-OC user do not significantly differ from each other. Okay. Similarly, on the second approach, what you can do is, after you observe the test statistic, which is 0.74, you can obtain a p-value. So the p-value is really two-sided. The probability under this distribution that observe this 0.74 are more extreme. So what is more extreme? That is more to the both distant side. So from 0.74 to the right side, the area is 0.23. And to the left side of negative 0.74, the area is 0.23 as well. So the p-value is really thus two multiply. So essentially you got the p-value of 0.46. And 0.46 is quite bigger than 0.05. So you fail to reject. Okay, so this is what we have learned for two sample t-test when you are willing to make the assumption of equal variance. What do? You first estimate a pooled variance estimate, and then you calculate this t based on this SP right here. And then what you do is you perform a hypothesis testing based on the t distribution with degrees freedom n1 plus n2 minus 2. The last scenario that we want to talk is, what if you don't know the two variance of the two populations, and you also do not want to make the assumption that they are equal? So in that case, it's actually also fairly straightforward is if you do not willing to make the assumption that they are the same, so what should you do is you just plug in S1 and S2 separately. So instead of SP here, you just put S1 squared over N1 plus S2 squared over N2. So that's quite similar to what we wrote here. It's like if two samples unequal variance, the only difference is the denominator. The numerator is similar to before, and previously you are willing to make assumption that S1 and S2 they are both the same. So because that assumption, you can use SP to substitute S1 and S2 because they are the same. But now you don't want to make that assumption. So what do? You do not substitute. You put S1 over N1, S1 over N1 plus S2 squared over N2. So it's the same format, except the only difference is you do not use a pooled estimate. So this is your T statistic. And after that, there is another price that you need to pay by not willing to make that assumption. And that price is the degrees freedom. Essentially, previously, because you assume they're all the same, so the total degrees freedom is sample size of the first sample plus the sample size of the second sample subtract 2. Currently, because you do not want to make the assumption, your degrees freedom has to make some trade-off, which means your degrees freedom has to be reduced a little bit to accommodate that you are assuming those are separate. So what is the degrees freedom? It's fairly complicated, but the good news is you don't need to remember that. You just need to understand that this V is a formula to calculate the standard the degrees freedom, and it is some number that below N1 plus N2, that less than N1 plus N2 minus 2. Okay? So the confidence interval is the sample mean difference plus or minus this T distribution plus this standard error, which is the denominator term right there. Remember, this T here has a degrees freedom, which is by that formula, calculated by that formula. So let's put that in an example again. Suppose you have two groups of the same question. It's actually not the same question. Actually, suppose you have two groups and you want to compare their mean of the two population. So sample size is 100 versus 74. N1 is 100, N2 is 74. And sample mean is 207 versus 193. And then you have a sample standard deviation 35 versus 17. So in this case, you can see that the sample standard deviation is quite different. And suppose for some reason that you do not want to assume that they have the same variance of the two population. The group 1 is the family that from a father who died of heart disease. And the group 2 is a family who have a father that is alive and do not have heart disease. And suppose you want to test the mean cholesterol level of the two group at alpha equals 0.05. Okay, so it's the same under that you first frame the null hypothesis and then its alternative and have the alpha level 0.05. So at this moment, you need to calculate the degrees freedom. What is your degrees freedom now? By this formula, it's a function of S1 and S2 and N1 and N2. So if you plug in all those numbers, you got this formula 151.4. Remember, degrees freedom, you just take integer, which is the closest integer to this one, which is 151. So what does that mean? It means that for this t-test, without assuming equal variance, the t-distribution is with 151 degrees freedom. Remember what you said here. N1 is 100, N2 is 74. So if you're willing to make the assumption, the degrees freedom is 174 minus 2, so it's 172. So here, because you're not willing to make assumption, you lose about 20 degrees freedom. So given this degrees freedom, from a t-table, you get that the z value is 1.96. You can actually see that this doesn't really make much difference because 1.96 is actually very similar to a standard normal distribution critical value. So, and then we calculate the t statistic by the previous formula. The only difference now is we separately plug in S1 square and S2 square by those two numbers, and we get 3.4. So 3.4, if you look at this distribution, it is right here. So it's in the rejection region. So what is our decision is to reject alpha at 0.05. And the conclusion is the mean cluster level for those two population of children is different significantly. Here, this slide actually is a redundant one. You can ignore this. This slide actually addresses how do you use F-test to compare the sigma 1 and sigma 2. We're not going to touch on that. So, as a summary, what we have talked today. We talked about two population inference or two sample inference today. And two sample inference, the first conceptual fundamental difference is you have to really be clear about your design, whether it's a paired design or it's an independent design, because that decision directly decides what test you're going to use. And here we talk about that if it's a paired design of matched or related to populations, you need to use a paired two-sample t-test. And then if it's two independent populations, you can use two-sample t-test. And two-sample t-test, there's a little bit of wrinkle in terms of whether or not you are willing to make that assumption that about the variance of the two populations. If you're willing to make that, the convenience is you can use the pooled standard error or standard deviation estimate, and you can use the degrees freedom with N1 plus N2 minus 2. If you're not willing to make the assumption, what you need to do is you need to, when you calculate your t, you need to plug in separate estimate of T1 and T2, and then your degrees freedom is a compromise, and you need to calculate that from your sample. I mean, so essentially from last time until this time, what we talked about is hypothesis testing. We talked about three scenarios, and essentially we talk about hypothesis testing on one question, which is population mean. For this one, if it's a one population, so you're talking about whether mu equals to some fixed value. That is your null hypothesis. And for this one, we talked about to use one sample t-test. Remember, the assumption is either the population is normally distributed or your sample is large enough to use central limit theorem. And then today we talk about two populations, right? And two populations, there are two scenarios. If the two population is related, what does that mean? That means it goes back to paired two-sample t-test. And essentially, paired two-sample t-test has an implicit relationship or implicit fundamental concept of one sample t-test on the mean, on the difference, right? And then the next scenario or the different scenario is two independent populations. For two independent population, it's called two-sample t-test. And slight difference whether you use the same variance or different variance. And that relates to the degrees freedom on how do you construct the t-statistic. Okay, so those are the three scenarios that we talked about. One population, two population, related or independent. And remember, all we have talked today is based on population mean. And everything that we talked, whether it's one or two population, the assumption is normal distributed or central limit theorem, which means n has to be large enough. Okay? So in your own practice, you will see that what if this or this and this doesn't hold? What should we do? And that goes back to the last lecture on non-parametric. Test. So if this doesn't hold, if those two assumptions doesn't hold, you need to use some non-parametric assumption. But essentially, under those assumptions, we gave you three tools from those two lectures. One sample t-test, paired two-sample t-test, and two-sample t-test. And all of those tools are related to population mean. For this lecture, we're now going to talk about population proportion. So let's see, if you want to test that p equals 1/2, or if you want to talk about whether it's one population or it's two population. Let's see, you want to talk about p equals to 1/2, that's one population. If you want to talk about p1 equals to p2, let's see, the prevalence of breast cancer is the same for Asian population and the American population. If you're interested in those type of questions, it's on population proportion. That is different from population mean. And if it's different, that means you cannot use some t-test on any of those. So for this, the test that you're looking for is called one sample proportion test. And the test that you're looking for here is called two sample proportion test. We do not have time for this lecture, for this course, to go into the details, but those are the terminology that you need to be clear, and I also want you to be clear, conceptualize that if you're interested in testing population, anything on proportion, you cannot use two sample t-test or one sample t-test, because that is quite, that is mistake that quite commonly encountered, okay? And then from next lecture, we're going to talk about Anova. So what is Anova? Anova really gives you the tool that, what if you have more than two populations? What if I have 3 or 4 or even more population? And I still want to compare population mean. So it really just expands this chart into bigger than 2 populations. And for that, you need to use Anova. Okay, so that is next lecture. And the next lecture after that is what we call categorical test. Categorical test or categorical data analysis. So for that one, it essentially tells you how to analyze frequency table or frequency data. That when you are not interested in mean, you're really talking about categorical variable, which everything is falling under frequency. What do you do? Okay, and so and then we have a non-parametric test, which gives you some tools that if those assumptions doesn't hold, what should you do? And last but not least, we will spend 1 lecture in talking about regression and association and correlation. So regression and correlation is tackling completely different question. Here, whether it's population proportion or population mean or frequency difference, the key fundamental concept or the key fundamental task is to detect difference. Okay, so that's the whole, that's the whole content of what we introduced until the last lecture. The last lecture is what if you're not interested in terms of difference, you're just interested in terms of correlation of the first population compared to the second population, whether it's some mean or some other parameters, what should you do? And for that one, it's called correlation and regression. And from that one, you can actually see there's a little bit, like conceptually, the connection between this one and the previous lecture, but it's on different tasks. So this is the whole structure of this course. And what we have finished today is hypothesis testing on population mean. And previously, the 2 lectures on estimation is also about population mean. And that is the estimation of population mean. And in addition, we have extra time to go to the estimation of population proportion. Okay, that's it for today. Yeah.
So let's say you're analyzing clinical trial data, and you have so like in the first example with that parent data, right, where you have to follow up.
Yeah.
Sometimes you're not going to have patients that continue to take the drug,
Yeah.
or whatever. When you calculate your N, you still include the